Hi everyone. I'm Yael Balla, as he said, VP R&D at karmanow.com. You're welcome to check out our cool product. So I will skip the introduction because he said already. But anyway, if you want to contact me, this is my personal email or LinkedIn. So let's start. But before we'll start, this talk title is Node.js garbage collector, but I owe you an apology. There is no such thing as Node.js garbage collector. This is because Node.js is actually using V8 under the hood in order to run JavaScript code. So the garbage collector that we'll be talking about today is V8 garbage collector, these small things there in the corner. Let's talk about garbage. What do I mean when I say garbage? Every time we create an object, a memory needs to be allocated for it. And when we finish using it, this memory should be cleared. In low-level languages like C or C++, the developer needs to handle it themselves. But luckily, we're using Node, and Node using V8, and V8 has a garbage collector that is freeing the unused memory for us. When I talk about memory and garbage and allocating object, where are these objects stored? In general, you can take the memory and divide it into two segments. One segment is the stack, where all the static data is located, the program method call execution, and all the primitive values. And this is also where we store the pointers into the object that we dynamically allocate on the heap. In V8, on the memory, there are different spaces. Each space is composed of pages. A page is a continuous chunk of memory that is allocated by the operating system. And we'll drill down into the different spaces later and what is stored in them. So garbage collector needs to free objects that are not in use. But how can we tell an object is not in use anymore? The first method that you may be heard of is something called reference counting. In this method, on every object, we have a number. And this number indicates the number of references to this object. Every time we create a reference, we increase it. Every time we remove, we decrease it. And when this number reaches 0, amazing, this object is no longer in use, and we can clear the memory. However, this can cause problems in case of circles in place of internal references that were not removed. In this case, even though this cycle of object is it's not reachable from anywhere from our application, it is still not cleared because it looks like it may be in use. And this is what eventually can cause memory leaks. What does it mean, a memory leak? It means an object that will never reference and we don't need it anymore, and that stays in the heap, and that over time the heap memory is filled in with such objects, and you don't have any room to allocate new object that you need now. Therefore, modern garbage collector today use something that is called tracing garbage collector. What is a tracing garbage collector? It means that we search for objects, and if we find them, it means they are in use, and if we don't find them, it means we can throw it away. They are garbage. And how this is done? In V8, V8 uses an algorithm called tree-color marking, and it is using tree colors to mark the object. It is done by attaching 2 mark bits into each object for coloring this object: white, gray, and black. And we also need a marking work list in order to track what we visited and what's not. So at first we scan the routes and we add them to the work list. And And every gray object becomes black when the collector pops it from the marking work list, visiting all its pages, all its children, and adding them to the tracing list as well. And then eventually all the object becomes black, and everything that is white, it means that we don't need them anymore. They are not reachable, and all the black objects are the live objects, and this is what we want to keep. So one problem that we have after creating object, deleting object, creating object, deleting object, is eventually the memory became fragmented. And for that, from time to time, the garbage collector also needs to run compaction. It means to copy all the object into the one side of the page and keep the rest of it empty. This is done in order to handle the case where a very large object should be allocated, and we need enough space in order to allocate it. Amazing. So problem solved, right? We can all go home. We know how to find objects that are in use. We know how to compact the memory. That's it. It sounds perfect. However, what the problem is that the garbage collector is not running in void. Eventually, it is running with your application, and it needs to clear and move object around while the application is mutating it. So this can cause problems. This is why usually the garbage collector needs to stop the application execution, handle the memory, and then continue. This is also what's called stop the world garbage collector. If this pause in the execution is short, then we don't really have a problem because no one will notice it. But if this pause is very long, it can cause performance issues, and eventually it will look like the server is unresponsive for a while until it will go back to normal. One of the ways to optimize the garbage collection work is to make this work in parallel, meaning having several threads that going over the memory and finding the object. It is more complex because you need to synchronize between the different threads work, and but eventually it will give you a lot faster execution. Another optimization would be to make the garbage collector completely concurrent, meaning not to stop the JavaScript execution and having the garbage collection work on different threads without stopping. What the problem with that? Of course, that as we said, the application is changing the object. The garbage collection needs to know the object state. So in order to make sure they work together, we need to synchronize between the JavaScript code and the garbage collection code, and this can cause some complexity. In order to synchronize, we have something that's called write barriers. Write barrier, it means that every time that you add a reference to an object, for example, calling object.field equals value, another object, you need to notify the garbage collection. Because if the garbage collector is currently doing the marking process, it might lose this object, and then this object will consider it garbage. So with the help of a write barrier, if someone adding a reference to an object, we immediately mark it as gray and add it to the marking work list in order to make sure that it will not be skipped. Another way to optimize garbage collection is something called generational garbage collection. Generational garbage collection is dividing the object to different groups according to the object age. Each group is, of course, called generation. Why do we care about object age? Why does it matter? This is because something that's called the generational hypothesis. It means that most objects die young. Think about it. You have a method, and this method, you're going to the database, you're querying a lot of objects, and eventually you doing some calculation returns true, false, right? All these objects during this method execution are now garbage. You don't need them anymore. And on the other hand, the objects that are used all the time, like globals, like cache, connection pools, things like that, it's very likely that they will survive until the end of the program execution. So by dividing these two types of objects, the young generation and the old generation, we can apply different algorithm for each type. On the young generation, we can take an algorithm that is optimized for a case where most objects are dead. And for the old generation, we can take an algorithm that is optimized for the case where most objects are alive. Now, V8 garbage collector, how does that work? V8 garbage collector is a generational garbage collector that is parallel and mostly concurrent. What generational we know, parallel we know, concurrent we know, but what is mostly? Mostly means that V8 tries not to stop the program execution whenever it's possible, but sometimes it has to. V8 is dividing the garbage collector work into two separate garbage collectors. One is the minor GC, which also called the scavenger. You might heard of it. And this is the part that is handling the young generation. And there is a specific space that is allocated from object of the young generation. It's called the new space. And the major GC that's responsible for the whole heap is using an algorithm called mark sweep compact. And when objects are moved to the old generation, this process will be responsible for clearing them. How do we move between generation? Every time we have a new object allocated, it is added into the young generation, and it's something that it's called nursery. V8 keeps on each object the number of GC cycles this object survived. At the beginning, the count is 0 because this object was just generated. After the first scavenger run, it is increased the counter. So now we know this object survived 1 GC cycle, but this object is still left on the young generation space. On the next GC cycle, the object will be moved to the old generation because we know that it survives 2 GC cycles, which means that it will probably survive for a longer time, and we don't want to scan this object over and over again. And from now on, the major GC will be responsible for checking this object status. The scavenger. So the scavenger is the minor GC, and it kicks in a lot of times, very frequently. And it kicks in when there is not enough space in the young heap to allocate a new object. V8 actually waits until there will be no space, and only then kicks in the minor GC. The scavenger is using an algorithm called copy collector. How many of you heard about it? Copy collector. Okay, I see some hands. In copy collectors, we have 2 spaces. One is where we allocate the object. This is what's called from space. And the second space is always empty. And when all the space on the from space is over and we don't have where to allocate new object anymore, then this is where the copy collectors kicks in. First, it needs to find all the objects that are live. We know how to do that using the same marking that I showed earlier. Then we said that each object has a count of how many GC cycle it survived or not. And according to that, the copy collector knows what to do. All the objects that's already survived 2 garbage collectors will be moved to the old heap, and all the new objects that were created from the last GC cycle will be moved into the 2 space. And now we have all the objects that we need in the 2 space and in the old space, and we can clear the from space. Everything there is considered garbage. And now the copying collector is actually switching between the to space and the from space. And the only thing that is left is to update all the pointers to point to the right location of the object, to the from space, and we are back to square one, where we have all the object allocated in the from space and the to space is kept empty. The scavenger is working in parallel. It still stops the program execution, but it is dividing the work between parallel threads. Each thread is doing all the actions that I explained, copying within the young generation, promoting to the old generation, and updating the pointers. Why is this a good choice for the young generation? We said copying object and updating reference is expensive. We have half of the memory empty all the time. So why is this? Why should this be quick? This is because what we said on the young generation, most of the objects are actually garbage. So we'll have only few objects to copy. And this is why we also don't need a lot of memory allocated for the young generation. And this algorithm can be very, very efficient. Now let's look on the major GC. The major GC is using mark swift compact. What is marking? Marking is the same that I showed earlier, the tricolor marking. And marking is done concurrently to the program execution. First, V8 stop the execution, start the marking, traversing all the routes. And then the marking is done concurrently with several threads with the help of write barriers, as I explained. And after all the threads finish their work, the control is moving back into the main thread, just checking which objects are still were changed and still left to scan. And after all this work is finalized, then we can move to the next phase. The next phase is called sweeping. Sweeping is done by finding the dead object and recycling their memory. We don't delete the memory, we don't move the object around. All we do is just keep reference to this empty space into something that it's called a free list. And then when we would like to allocate new memory, all we need to do is go into the free list, find a space with the right size that we need, and allocate the object there. Of course, that after a while, like we said, the memory becomes fragmented. So V8 keep track on each page, and when a certain page became fragmented, it compacts this page, and not all the memory is compacted together. Each page is compacted separately on a different head, which makes the overall execution very efficient. So this is a summary of how the major GC works. First, the marking is started in a concurrent to the JavaScript execution. V8 actually always validating the memory status, and when it feels there is a memory pressure and we need to start, and soon we will need to increase the memory, then it kicks in the marking. And when the marking finishes, then the sweeping start, and in parallel we're also doing the compaction of the different pages. And when all the compaction is done, we can go back to the JavaScript execution, and sweeping can still be done while the application is running. So now let's see a short live demo of how it looks with a short script that I've made. Okay, so this is a very simple JavaScript code which create 1 million object, adding them to a list, And after every time that I'm creating an object, I'm also popping it. It means I also remove the reference to this object. I'm running this node script with two flags, inspect and trace.js, in order to see the garbage collection debug messages. It runs really fast. But what we can see here is that we can see the time that the garbage collections kicks in, and we can see that the scavenger, which means the minor GC, is the one that is running, and it's relatively managed to keep the memory size low, from 5.6 megabytes to 4.9, from 7.5 megabytes into 5.9, and eventually the application execution is finished with 12 megabytes of memory, and we don't even have a GC, a major GC here. But now let's see what happens when I comment out the object pop method. What it means is that I keep a reference to every object that I created until the program execution ends. Okay, so let's see what happens now. Now it starts the same. The scavenger kicks in and it's trying to free in the object, but we can see here that it's not really working. It's moving from 8 megabytes to 7.8 megabytes, and then afterwards we reach to 23 megabytes, and at a certain point the mark compact, which means the major GC, kicks in, and it's managing to free some memory from 47 megabytes into 37, but eventually I'm still referencing all these objects. So we finish the program execution with 99 megabytes of memory used. So what can we learn from this demo? We're actually learning that the garbage collector is not a mind reader yet. If you keep reference to your object, then it will not be able to clear them. So pay attention to what you store on the globals, what you store on your cache, in order to help the garbage collector to help you. So this is it. This is the end. We talked about what a garbage collector is, some common terminology, and how it works in V8. Hope you enjoyed the live demo. And if you have any questions, I'm here. Thank you.